In question 6, you're given this table here which tells you how many cars are sold in each year, and it breaks it down into each quarter as well. You're also given the engine types of those cars. This part doesn't come in until a little bit later. In part 1 of this question, you're asked to represent some of this data on a suitable chart. So first of all, the charts you have to know are the stem and leaf plot. If we try and do a stem and leaf plot with this data, then you're going to end up with stems that are these 5 numbers long, and then a leaf is just going to be the 1 number long. We're going to end up with 1 stem and 1 leaf per year, and arguably that should be represented on 6 different stem and leaf plots as well, because the year is also varying. So the stem and leaf plot probably is not the best way to go here. You could do a histogram, and that should be fine. Depending on who you ask, this could be continuous data or it could be discrete data. The time is continuous, arguably, because it doesn't particularly stop at any point. You could also think of it as being discrete, because what we're actually representing here is the annual total per year. This is the variable that is really important here, and the year is just an extra description for that information. So after histogram, you could also do, say, a scatter plot where year is probably the best one to go on the x-axis, and then the annual total will go on the y-axis, and that would be fine as well. A pie chart is probably not the way to go. That normally represents that would represent, say, a single year, and represent some kind of breakup within that year of how you're going to split up the data somehow. I went with a bar chart then. It's almost the same as a histogram in this case, except a histogram tends not to have these gaps between them, whereas bar charts do. So it'll work very similarly. I'm just showing how many cars were sold in 2006. It was in around 170,000, which would be the height of the y coordinate. In 2007 it was about 180,000, so again, just having the height of my bar at about 180,000. And that's pretty much it. That should be the whole part of that question done then. In part 2, you're asked to find the mean number of cars sold per year over the 6 years, and you can just find the mean formula on page 33 of the Formula and Tables book, and it'll just be this, where this letter mu represents the mean. This means, the sigma means add up all of the extras, just the number of cars in this case. So you add up all the number of cars in each year and divide by how many data points you have, and we have 6 data points in total. So I just go ahead and do that. I add up the 173,273 from 2006, 180,754 from 2007, and just add up all the rest of them as well, divide by 6, and in total you get 121,128. Part 3 has you calculating the percentage increase in annual car sales between 2009 and 2011. Well, the increase is just given by the difference in those two car sales divided by the original amount of car sales, and then multiplying by 100. So it's 86932, that's the number of cars sold in 2011, minus 54432, which is the number sold in 2009, and I'm dividing by 54432, which is the same as this one. Just be careful that you're dividing by this number, the number from 2009, because you're comparing how many were sold in 2011 to how many were sold in 2009. So you're using the 2009 as your basis. So that's why you would use this number. So you multiply that by 100 and you get 59.7%. In part 4, these two people, Eva and Paul, both make some statements about how well the car sales are going. Eva says that they're going well, Paul says that they're not really, and Paul supports his argument with a bit of data. And you have to complete these two sentences, that Eva's argument doesn't recognise something and that Paul's argument doesn't recognise something as well. What you're really being asked to do is to take a look at the figures over these years and just make some comparisons about that yourself, and then apply those comparisons to Aoife's and Paul's statements. In terms of critiquing Aoife's argument, then she's saying that the car sales are currently going well, so you just have to see, are they going well? So in 2011 they're at 86,000 or 87,000, They used to be more than double that, 173,000, 180,000. So they're probably not going well then, because they've fallen by, they're less than half of what they used to be, at least in 2006 and 2007. So, and they are going well compared to 2009 though, so she does have some point. Perhaps she's just not looking at all of the data, or perhaps she has access to other information that we don't. So these are the kind of things you would write, that the long-term car sales are low, the car sales are only good compared to 2009 and onwards. Agreeing with her, then, that's more the other point, that when you have to critique what Paul's argument says. In terms of critiquing Paul's argument, then, he's saying that the sales are not going well. He backed it up with saying that the sales have fallen by 52% since 2007, so going from 180,000 to 87,000 or so, that's a fall of 52%, and that they're below average. Well, you worked out the average previously, that it was 121,000 or so, so yeah, they are certainly below average. So he's certainly backing up his statement quite well. We only have access to these 6 years. It's entirely possible that, that these 3 years here, where they're quite high, they might be quite extraordinary numbers, that compared to previous years, there were nowhere near that many cars sold. That maybe that sort of 80, 90,000, those kind of numbers would be quite normal. So there's a few things that you could say, that the car sales have risen by 60% since 2009, and that the car sales may actually be quite good. There's a nice buzz phrase there you can use, given the economic climate. It's quite a nice phrase to use at the moment, given all the recession and everything like that. In the next part, you're asked to give a more balanced description of the pattern of car sales, and it's certainly no harm to try and back this up with some percentages or figures or something like that. So you could say, for example, from 2007 to 2009, they fell by 70%. I say 2007 rather than 2006 because the 2007 was the peak year. And then you could also say they've seen an increase of around 60% since 2009. So the more balanced description is that they fell, but they've recently come back a bit. It's hard to say whether they're going well or badly because we don't have very much data to actually work with. So the balanced description really is just including as much purely factual information as you can, and as I say, including percentages or any kind of numbers in there is certainly going to help your case. Now we have to describe how the sales of cars are distributed over the 4 quarters. When they say quarters, they mean 3 months of the year at a time. Normally they're done like this, January to March being the first quarter, as in the first 3 months, then the next 3 months, April to June, be the second quarter, and so on. Your question is to describe how the sales are changing between each of these sets of months. If we take a look at the data, then we can see that the first quarter seems to pretty much always have the highest number of cars sold. The second quarter, again, tends to be higher than the third, and the third also tends to be higher than the fourth quarter. So most of the sales are sort of towards the start of the year. And a good word to use here to describe how the data is distributed is skewed. And remember, the way you use skewed is towards where the lowest numbers are. So in each case, the last quarter is sort of where the lowest figures are. So you say that the sales are skewed towards the last quarter of each year then. Next, you're asked to suggest a reason that most of the cars are sold sort of in the first couple of quarters of the year. And this is a nice, easy question. You can come up with absolutely anything. For example, the ones I have here are that people like to have a new registration on their new cars. In other words, if you buy a car in January, then you have your 2012 registration for 11 months, where if you buy it in November, then you only have it for 1 month, or that kind of thing. And people also like to have the low registration numbers, so they would rather have a car in the first 10,000 sold that year than in the last 10,000, that kind of thing. You could say that people want to have their new cars by the summer, or maybe they're spending the last bit of their Christmas bonus, or it could be absolutely anything really. It's a very, very nice question. You can just pick up nice easy marks on it. In the last part of the question, you're told the sales for the first quarter of 2012, and you have to estimate how many cars are going to be sold in total in 2012. There are a number of ways of doing it, which are all equally valid, and some of them are kind of the same. For example, you can say that the number sold in the first quarter is a certain percentage of the number sold throughout the whole year. You can say that the number sold over the whole year is some multiple of the ones in the first quarter, which is the method I'll show you in a minute. It could be pretty much anything really. You could even try adding on the numbers, so that, say, the annual total there is 100,000 or so more than in the first quarter, and the same is true in 2007. It's not as true in 2008, so maybe that method isn't quite as good. So here's the multiple method. So this is how many cars are sold in total in 2006, and this is how many are sold in the first quarter. So the total, or the multiplication factor, is 2.28, so you do that for each of the 6 years. Find the average of those, which is 2.12. If you want to just maybe throw in an extra mark or two, you can work out the standard deviation there just to check how well your method actually fits. And in this case, the standard deviation is about 1/10 of the mean value, so that's pretty decent then. So you can use that to work out the estimate for total number of cars sold in 2012. And if we go back to our actual data set, then you can see that we start out with 36,000 or so, which is sort of in around this range, and our estimate is at 79,000, which is not too far from here. So it's a pretty decent method to use, I think, anyway. So it should get you pretty much all the marks, especially if you include that standard deviation bit. Next, you're given two pie charts, one of which has already been filled in and represents the engine type of the car sold in 2006, and your question is to fill in the second pie chart, which represents the engine type of car sold in 2011. So this is the data from 2011. There are 86,000 in total, or thereabouts. 23,000 petrol, 61,000 diesel, and about 2,000 other. So first of all, you need to work out what kind of angle they would take up, or what percentage of the circle they would take up. Well, you just use this formula here where the angle is given by the number of, say, the number of cars of a certain engine type divided by the total number of cars sold multiplied by 360 degrees. And if you wanted to work out the percentage of the circle, you would multiply it by 100 there instead of 360 degrees. This is what you get. Say the angle for diesel is the 61730. That's this number here, the number of diesel engines sold in 2011, divided by 86932, which is the total number of cars sold in 2011. Multiply that by 360 degrees, and you get 256 degrees. You do the same thing for other, where you take 1956 as being the total number of other engines sold, and 23246 is the total number of petrol engines sold, and you work out the angles for each of those, or the percentages. If you do the angles, they should all add up to 360 degrees, or depending on how you round it, you might get 359 or 361 or something. And if you're doing in percentages, then they should add up to 100, or again, depending on rounding, you might get 99 or 101 or something like that. In the end, this is pretty much what you should get. The petrol, I have it written here as a percentage, but that's 96 degrees, and you just use a protractor to draw that out. Other is 2.3%, that's 8 degrees, and diesel is 71%, which is the 256 degrees. In the next part, you're given 5 statements, and you have to decide which of those statements best describes the the data. Now you have to be very careful with reading this question. I got it wrong the first 2 times I tried this question, and I'm fairly sure I have the right answer now. So it says, which of the following statements best describes the change over time in the popularity of diesel cars as a percentage of the total? So first of all, you need to work out the percentage of diesel cars sold as a percentage of the total, and you have to work out how that percentage is changing over the 6 years. So this is what you get when you work all that out. This column here is the percentage of cars sold that are diesel, and it just comes from the table. This is the 44,000 divided by 173,000 that you're given in the table, and same with the rest of this column. And I have another column here which is an increase, and I'm measuring that in percentage points as opposed to any kind of percentage. It'll be a little bit easier that way. And I think it's more representative of the data. So, of course, there's no increase in 2006 because we don't have any years before that to compare it to. In 2007, then, the percentage of sold was 28, which is 2.6 percentage points higher than 25.4. Then the next one is 6.3 percentage points higher than the 2007. In 2009, there's a huge spike, which is 22 percentage points higher, and so on. So, which of these statements describes that there's always an increase, and in 2009 there was a bigger increase than normal? Well, the first one here is that diesel cars have suddenly become very popular in the last year or two. Well, not really. I mean, they are more popular now than ever, according to this data at least. But they haven't suddenly become very popular, really. It's been generally a steady increase, and I mean the biggest increase was more than 2 years ago, so A is out really. And B, the diesel cars have increased very steadily in popularity over the last 6 years. It's been fairly steady. It's normally sort of less than 10 percentage points of an increase each year, but in 2009, as I say, there was a huge increase of 22 percentage points. So B is out as well. And C, diesel cars have become very popular since car sales started to improve. It's very similar to A, because car sales have begun to improve in the last year or two. So for the same reasons, C is not the right one. Diesel cars got more popular each year, with an especially big increase in 2009. Well, that's exactly the case. The percentage of diesel engines sold has been increasing every year, and in 2009 there was an especially big increase. So it's probably D, but we'll just check E to be absolutely sure. Diesel cars became popular as the car sales fell, but have been getting less popular as they rise again. Well, that implies that there is a decrease in popularity, which there isn't when you look at this data set. So just to be double check again, there's always an increase, and in 2009 there was a massive increase. So we're looking at D being the right answer then. In part D, you're given this table of results that the CO2 emissions in grams per kilometre from both diesel engines and petrol engines. And part 1 is to construct a back-to-back stem and leaf plot based on that data. So first of all, just remember, a back-to-back stem and leaf plot is going to display both diesel and petrol at the same time. Secondly, the leaf of a stem and leaf plot can only ever contain one digit, a single digit separated by commas, and that represents several numbers. So the stem takes all of any other digits that are in the number. So let's say these ones are all 3 digits long. So the stem is always going to be 2 digits, and the individual leaves are going to be single digits separated by commas. And of course, don't forget your key at the end as well. This is what the diesel side of the stem and leaf plot is going to look like then. Firstly, when constructing this, it's no harm to rewrite your data here in ascending order, because your stem and leaf plot is going to be in ascending order. Say that this one here, the 107, is first, then there's 110 is going to be the next smallest, there's 114 there, and so on up to 134 is the highest number there. So when I write the 107, I put in the 10 in the stem, and the leaf part is only ever a single digit, so there's the 7. And this key here tells you how to read it. If you see a single digit, the line separating stem and leaf, and 2 digits like that, it means you read it this way. The 2 digits first, the single digit, and it's in grams of CO2 per kilometer. So that's how you read this one. That's 107 grams per kilometer. And same with the rest of them. Again, this line here, it's single digits. They're all separated by commas, and you can see they're in ascending order as well. And so you read these as being 110, 114, 118, 119, and so on. And again, the next stem is all the numbers that are in the 120 range. So there's 120 there, 125, and 125. Lastly, 134. And you know, in your table there are 12 numbers in total. So in your stem and leaf plot there should be 12 numbers as well. So there's 1, there's 7, that makes 8, there's 3, which is 11, and 1 more, which makes 12. So I've definitely included all of my numbers there. Next, we do the same thing for the petrol engines. Again, it's no harm to rewrite your data here in ascending order. So you end up with 129 being the lowest one, and in fact there are 3 of those, 3 of the same number, and 159 is the highest. So you write that on the other side. Remember, diesel was I put on the left. It doesn't really matter which one you put where. So I put diesel on the left, so I'm putting petrol on the right. So I'm separating my data into 2 different parts. Well, it was given in 2 different parts, and I'm keeping it in 2 different parts. I put in my 129s like this. There's the 12 in the stem, or which refers to 120. Then I've got 3 9s, which means I've got 3 129s in total. Then I have, say, 133. I have 138, and down here I have 157. And again, this key here tells you how to read it. It's a different key to before. Remember, on this side, it was a 7 a line, and a 14 meant there was 147. In this case, it's the other way around. I've got the 14 on the left, then the line, then the 7, and that means 147. Of course, there isn't 147 in this table at all. It doesn't really matter what numbers you choose, as long as it represents how to read your stem and leaf plot. In the next part, you're asked to say, based on your stem and leaf plot and based on any calculations you perform about central tendency, do diesel engines produce lower CO2 emissions than petrol engines? And remember that this data here is just representing the CO2 emissions in grams per kilometer. So first of all, just remember what central tendency means. It's any kind of average. The 3 to look at particularly are the mean, which is when you add them all up and then divide by how many data points you have. Then there's the median, which is when you arrange all your numbers in ascending order and then pick the middle one. And there's the mode, which is the number that occurs most often. In terms of your stem and leaf plot, you can get your median and your mode from there. You could also potentially talk about the sort of range / frequency aspect of it as well. So, you know, in terms of diesel, there's one number in the 100 to 110 range. There are 7 numbers in the 110 to 120 range. That's also sort of a measure of central tendency, and it's very evident from your stem and leaf plot, as opposed to the table, what way the numbers are laid out. So here are a few calculations that you can do on that. To find the mean of diesel, you add up all the numbers and you get this 1,424. There are 12 pieces of data in total, so you divide by 12 and you get 118.7. The median you get, in this case, because there are an even number of data points, you can't just pick the middle one, so you take the mean of the 2 middle ones. In this case, the 2 middle ones are 118 and 119, so their mean is 118.5. The mode is the number that occurs most often. 119 and 125 both occur twice, so they're both the mode. There are 2 modes for that data set. In terms of petrol, then, you do the same thing. The mean is 139.3. Again, that's grams per kilometer. I should have that written. The median is 137. Again, taking the 2 middle numbers, in this case it's 136 and 138, and finding their mean, which is 137. The mode being the number that occurs most often is 129. So in fact, for each of these measures of central tendency, the CO2 emissions for diesel are lower. So you can see, comparing the means, there's a difference of about 20 grams per kilometre. In terms of the median, again, it's roughly 20 grams per kilometre in the difference. It's a little bit tougher to say the same thing with the mode, but I mean, both of these modes are lower than the single mode that appears for petrol. You can talk specifically about your stem and leaf plot as well. You can see that, for example, diesel, there's a lot of numbers in this 110 range, and in petrol there's a lot of numbers in the 130 range. And the numbers seem to be sort of roughly towards that. I mean, in this case, there's 3 in the 129s. These 150s, they're not too far away from the 130s. So it's kind of like talking about the median, in that you're talking about some sort of middle number characteristic, but to some degree you're also talking about the variability. It's sort of like a standard deviation for the median as well, that you're saying that a lot of numbers are sort of towards the median or towards the middle number, or that a lot of your data points are sort of gathered around the same number. It's sort of a measure of central tendency as well. Of course, you're only given a few centimeters in the exam, so pick maybe 2 of these or maybe 3 of these to talk about, and you should get your marks and more, really. In the next part, you're asked to comment on the variability. So first of all, you can bring up that point that it was in the last part of the question as well, that a lot of the numbers are sort of towards the centre. But you can be even more specific than that with this question, because they're specifically asking about variability. So the things that you should be talking about are the range and the interquartile range, and you can use your stem and leaf plot as well to sort of say that the numbers are gathered together towards the centre. That's also sort of talking about variability as well. Again, we're just going to work with some calculations. The first measure of variability in terms of calculations is the range, which is just the highest number minus the lowest number. In this case, for diesel, it's 134 minus 107. So that gives 27, which it means that there's 27 in the difference between the highest CO2 emissions and the lowest CO2 emissions. So that just sort of tells you the spread of the data. Next thing is to work out the interquartile range. It's a bit tricky if you don't really know it. The first thing is to find the first quartile. You find, first of all, you have to figure out how many pieces of data you have, in this case 12. So you find 1/4 of that, and in this case that gets you 3. And for other numbers it will be different. Use what's called the floor function, which it takes whatever number you put into it and then it rounds it down to the nearest integer. So in this case 3 is already an integer, so we need to apply the floor function. In the cases where you do need to apply the floor function, it's much easier. For example, if we had 13 pieces of data, we take 1/4 of that and we have 3 1/4. So we apply the floor function to that and we get 3, which means that we take the third number in our ascending order, in the ascending order of our data set. But since we didn't need to apply the floor function, what we have to do is we take the mean of the third and the fourth numbers. And in this case, it's 104 is the third number and 106 is the fourth number. So we add them together, divide by 2, and we get 105. And again, if there were 13 numbers in total, then we just, because we apply the floor function to the 3 1/4, which is 1/4 of 13, and we get 3, which means we just take the third number. We don't have to find means or anything like that. So we do the same thing for Q3. In this case, we take 3/4 of the number that we were given. So in this case, 12. Take 3/4 of that, and we get 9. Again, we don't need to apply a floor function. And in the cases where we don't need to apply a floor function, we take the number that we have and the next one. So we're looking at the 9th number and the 10th number. In this case, in the case of diesel, 120 and 125. add them together, divide by 2 to find the mean, and that gets 122.5. And again, if there were 13 numbers in our data set, we take 13 and find 3/4 of that, then we get 9 3/4. Again, apply the floor function, which takes you down to 9, because you always round down to the nearest integer with the floor function, and that means you take the 9th number, which in this case would be 120. But since we didn't need to apply the floor function, we take 120 and 125, the 9th and the 10th number, and find their mean, and they get 122.5. And after all of that, to find the interquartile range, we take Q3 and take away Q1, so it's 122.5 minus 105, which is 17.5. We're going to do exactly the same things for petrol. We find the range, which is the highest number, minus the lowest number, 159 minus 129, which is 30. Again, because we have 12 data points, we find a quarter of 12, which is 3. We don't need to apply the floor function, so we take the 3rd number and the 4th number, find their mean, and it's 131. To find Q3, we have to find 3/4 of how many data points we have, so 3/4 of 12, which is 9. We don't need to apply the floor function because 9 is already an integer. So we take the 9th number, 139, and the 10th number, 150, find the mean of them, and we get 144.5. To get the interquartile range, we take the Q3 and minus Q1 from it. So we get 144.5 minus 131, which is 13.5. And this is a little bit interesting, that the range for petrol is higher than the range for diesel, which means that the data is more spread out. But the interquartile range for petrol is lower than that for diesel, which means that the data is sort of more centralized. There's a lot more data in the middle range